Hello everyone, welcome back to the fifth lecture of Applied Statistics. My name is Ulrich Weber. So today is going to be an exciting day because we talk about inferential statistics today. And it's going to be quite a conceptual lecture, lots of new concepts. It's going to be a bit tricky at times, but I've got lots of very applied examples and I'm sure we're going to get through it quite easily. So let's have a look. The first thing I want to talk about is the population and sampling. What is the relationship between those two? So in the first chapter of this first lecture, we talked about data. So we've got a sample of data, and in there we calculate things like the mean value, different averages. We talked about variation. How do I calculate that? And then later on we started talking about random variables, and this is the bit up here, and the expectation values, the variance, different distributions. And now we basically want to put those two into proper context. What we have to be aware is the sample data that I have, it stems from the population, but it's only one sample of many. So we could have had a different one. There's some chance in it. Like the sample we've got, the data we've got, has some randomness in it, and chances are we could have gotten a slightly different one. Yeah, that's an important concept to realize. If we just think of the things we describe samples with, then we worked with a mean value. This is the mean value. I call it x bar for our n sample, and we talked about the variance, and in the sample I want to call the variance s squared, just to not confuse it with the population, where the expectation value is mu and the variance of our random variable is sigma squared. Okay, so we have to keep them separate. This identifier 1 here just means sample 1. Yeah, that's like a 2 here and so on. All right, let's make it a bit more applied. So I paint the same picture, just giving you an example. Let's say we've got a fair die, that's our system, and then obviously we know what our model or population looks like. We've got the numbers 1 to 6, so our expectation value is 3.5, exactly in the middle. 1 plus 6 divided by 2, and our sigma squared, our variation, is 2.9. Now we've done all this in previous lectures, how to calculate this. Now, if we roll the die 4 times, we could end up with the following samples. Like for example, we could end up with this sample 1, 3, 4, 4. So that sample exhibits a mean value of 3 and a variance of 2. So the mean value is a little bit off from 3.5, variance as well. Yeah, that's kind of what we expect. In a 4 sample, we have quite big variations. We also could have gotten something like this, like sample 3, 1, 2, 3, 6. Also random sample. Here we've got similar mean value, but a lot bigger variation. Now variance is too big. So all these different samples kind of have different values, and if we plot that graphically, all it means is each of these mean values I plot here. So this is x bar 1, for example. Now, and I've got those different ones. That might be x bar 3. So the mean values of each sample are at slightly different points. The true value might be here. This is mu. So all kind of lying around it. And what is also true, each sample has its own, let's say, distribution. Yeah, it doesn't completely reflect the random variable, the truth, but like sample 1 might have a distribution like that. You know, that might be like there are more 4s in sample 1, for example, yeah, than like we know that the true model has. So we see like different mean values, different distributions. So how is this ever gonna work? Well, fortunately, we've got the law of large numbers. There are two different ones, but I'm going to talk about that in a second. And the law of large numbers basically says if I've got n independent and identically distributed random variables, so-called IIDs, and we've got that, like if I roll the die multiple times, it's always the same random variable. And we calculate a mean value like this. Mean value of my random variable is the sum divided by n. Then the law says that if we have a large enough sample, so if we go n to infinity, so large sample, then mean value converges to expectation value. The mean goes to expectation value. So as long as the sample is big enough, we don't need to worry that there's like a little error in it. In mathematical terms, and there's the distinction also between the weak and the strong law of large numbers, there's like different types of convergence, which is not important to us at the moment. So basically they're saying the same thing. The weak law, which we have here, basically says this: if you go to very large no, the other way around, like if you imagine like a tiny difference k, yeah, imagine it like really, really small, let's say difference of 1 divided by 1,000,000, yeah, really small number, then but if we go to a large enough sample, there's a probability of 1 that the difference between mean and expectation value is smaller than this super tiny number k. Yeah, and we can do that with any k. So imagine an even smaller k than we just had. It doesn't matter, the probability is always 1 that we, the difference is actually smaller if you just go to large enough samples. Okay, so this is the first concept, and in the next video we're going to talk about variation, which is also very interesting.